creating movable classes. In this section, we're going to take a look at the reasons your classes should be movable, item emplacement in standard containers, how to write classes that benefit from move semantics, the rule of 5 and rule of 0, and lastly, we're going to have an example implementation of a bare-bones, movable, and move-aware STD vector clone. Let's begin with the first video, standard library support for movable types. In this video, we're going to take a look at the benefits of making your classes movable and standard library utilities that revolve around movable user-defined types. Begin by answering the questions. Why would you make your types movable and why would you spend effort on it? Writing classes that support move operations can greatly increase performance, safety, and expressiveness of your code, as we've seen in the previous sections. Also, this is the topic we're going to cover in this video, the standard library provides many utilities that make use of move semantics or are defined in terms of move semantics, even for user-defined types. Let's dive into the code. Almost every container in the standard library is move-aware. This means that it will use move operations, if available, when dealing with its items. Let's begin by looking at STD vector. Assuming that foo is one of your classes that supports move semantics, we can see that vector will try to move whenever possible. In order to prove this cheaply, I've added some print statements in the constructor, destructor, and copy and move operations of the foo class. In the first function, vector move awareness, we'll begin by instantiating a vector of foo and a foo instance f0 on the stack. Firstly, we'll push back f0 inside the vector, and this will obviously copy it. If we use std move, we'll convert f0 to an r-value reference, and pushback will detect it and move f0 inside the vector. The same will happen if we use pushback on a foo temporary. It will be moved as it's already an r-value. Let's try to compile this snippet and look at the output. Before doing that, let's reserve the vector so that the internal buffer resizing does not produce additional uninteresting operations. The output is what we expect. We see a copy when pushing back f0, a move when pushing it back using std move, and then a temporary being constructed and a move when pushing back a temporary inside the vector. Finally, every foo instance we created is destroyed. Let's now introduce a new concept, the concept of emplacement. Standard library containers allow us to go one step further compared to moving items inside containers, and allow us to entirely construct the items in place inside the containers. This operation is called emplacement and is supported by most standard library containers. Here's a simple class called bar, which contains int member field and a constructor that takes an int and initializes its member. In this function vector emplacement, we're going to instantiate a vector of bar, and then we're going to move a bar temporary inside the vector using pushback. Then we're going to use this new member function introduced in C++11, which is called emplaceback, which takes any amount of arguments and perfect forwards them to bar's constructor, which will construct the bar instance in place. We should be able to see that there is no move happening for the emplaceback call, as the bar instance is constructed directly inside the vector. In order to show the effects of emplacement when running this code snippet, let's first add some print statements to the bar operations. Also, as we did before, let's reserve some memory for the vector so that the internal buffer resizing won't affect the output of our program. We can now run our program, and we'll see something really interesting. When calling pushback, as expected, there's going to be a call to the bar constructor taking an int, and then the bar instance is going to be moved inside the vector. But when calling emplaceback, we won't see any move or copy operation. This proves that the bar instance is being directly constructed inside the vector. Emplacement works by perfectly forwarding all arguments passed to the emplaceback member function to the constructor of a bar instance that's being created directly in the target memory location inside the vector. Note that writing move-aware and movable classes is very important even if emplacement exists. Consider the case where we have a bar wrapper struct, which itself contains a bar and has a constructor using the passByValue and move idiom to initialize its member bar variable. In this example function over here, we are creating a vector of bar wrapper and then emplacing back a bar instance into it. Unfortunately, in the code above, there is no way that we can avoid the bar temporary from being constructed and moved inside the wrapper. This example shows that when you have more layers of indirection or wrappers, such as in the case of bar wrapper, it is beneficial to have move operations even if emplaceback and similar method exist, as you don't know how your class is going to be used, and providing the best possible code for copy and move operations is important to ensure the performance of your program. Vector is obviously not the only container supporting move semantics. All the commonly used standard library containers are move-aware and support emplacement. More examples include std_map, std_set, std_list, std_unordered_set, forward list, and many more. Containers are not the only important thing that the standard library provides, which heavily relies on move semantics. The standard library provides many utility functions and classes which are defined in terms of move semantics or heavily support them. Some common utilities that you might have used before, like std_swap, or some new utilities such as std_exchange, are defined in terms of move semantics. Generic wrappers such as std_pair or std_tuple will use move semantics whenever possible. And even algorithms can benefit from move semantics thanks to the addition of things like move iterator, which wraps an existing iterator, forcing it to move on every step. Let's now switch to the editor to take a look at everything I just mentioned. Let's begin with swap. Swap is a very versatile way of swapping into objects. Users can define their own specialization that can be found through ADL, but std_swap is always a valid fallback. Before C++11, std_swap was typically defined as follows. It would copy the first one to a temporary object, then assign the value of the second one to the first one, and finally assign the value of the temporary object to the second one. This works, but is incredibly expensive for a lot of types, which led container implementations to provide their own fast swap specializations. C++11 and above, swap is defined in terms of move semantics. You can see that it's very similar to the previous implementation, but instead of copying 3 times, it will attempt to move 3 times when possible. No copies are executed when using the default implementation of std_swap since C++11, and this is great both for library users and developers. As long as you provide sensible move operations for your types, std_swap will be automatically efficient. Let's now take a look at a new utility added in C++14. It is called exchange, and while it's similar to swap, it has a completely different role. The signature of exchange is as follows. It is a template function that takes a t and a u, which is defaulted to t. It will take an object by lValue reference and a new value by forwarding reference. Finally, it will return a new t instance. The semantics of std_exchange are as follows. It will replace object, which is the first argument, with the new value, while returning the old value of object. It relies on t and u supporting move operations. Here's a possible implementation. In this example implementation, the first thing we do is to temporarily store the old value of object inside the old value temporary variable. In this case, we use move to prevent unnecessary copies. Then we use std_forward to perfectly forward the new value inside object. Again, if new value is an arg value, this will move instead of copying. And finally, we return the stored old value. Since we're returning a local variable, this will probably trigger RVO, return value optimization. But even if it doesn't, it will just move the old value out of the function. As you can see from this implementation, if both t and u implement efficient move operation, std_exchange is a very cheap way of modeling replacement where the previous value is interesting. The most common use case for std_exchange is when implementing move operation for user-defined types, as it avoids a lot of boilerplate. This is another bare bones unique pointer implementation, which is obviously not complete and is here just for educational purposes. As you can see, it stores a pointer to an int, which is by default initialized to null pointer. It provides a constructor that will take ownership of an existing int pointer, and the destructor will automatically delete it for us. Copies are prevented by deleting the copy constructor and copy assignment operator. Now, you can see how std_exchange is really useful in making the code more readable and terser when dealing with move semantics. The move constructor of our unique pointer will change its own stored internal pointer with the right-hand side's pointer, and will also set the right-hand side's pointer with null pointer to prevent the memory from being freed twice. And std_exchange captures the semantics of this operation very elegantly. As you can see from this line of code, the first thing we do is to store the first value here, which is the right-hand side pointer, to some temporary location in memory. Then we assign null pointer to the right-hand side pointer so that it will not be free twice. And finally, we assigned the right-hand side pointer value to a member p variable so that the current unique pointer will take ownership of the memory location. With exchange, we can say that in one line without repeating ourselves. And this can be useful both for the move constructor and for the move assignment operator. One way of quickly remembering what exchange is doing is to look at it as a series of operations that are being executed left to right. If you read this line of code from left to right, you can see that p is going to take the value of rhs.p, and rhs.p is going to take the value of a null pointer. So that's a quick way of remembering the functionality of exchange. Let's now look at some generic wrappers. You have probably used either pair or tuple in your code before. They are general-purpose wrapper classes that bundle together objects of potentially different types. std pair is just like tuple, but is less general, as it only holds 2 elements. So for the rest of this code snippet, we're going to cover tuple. All observations will also apply to pair. Tuple instances can be created either explicitly by using their constructor or through std make tuple, which is a utility function that deduces the type of the objects for you. Moves are used whenever possible, both during construction and assignment. In this function, creating and assigning, we're going to look at some examples of creation and assignment of tuples. The first tuple t0 is created by explicitly specifying its type. It will be a tuple containing a foo, a bar, and an int. By using uniform initialization, we are default constructing the foo, the bar, and constructing the int with 1. The second tuple, t1, will be constructed by using std make tuple, which takes any amount of arguments and returns a new tuple with the types deduced from the arguments you pass to make tuple. In this case, the resulting tuple will have the same type as t0, a tuple of foo, bar, and int. Tuples can be copied using the assignment operator, and this will execute an element-wise copy. They can also be moved by using std move, and this will execute an element-wise move. You can retrieve items out of tuples and pairs by using std get. std get allows you to retrieve items either by index or by type. Let's begin by looking at the retrieval by index. In this function, I'm creating a tuple named t, which contains a foo, a bar, and an int. I can retrieve L-value references to the items inside the tuple by using std get and specifying the index of the item I'm interested in as a template argument. As an example, if I say std get of 0 of t, I will get back an L-value reference to the first item, which is a foo. I can also move items out of a tuple in 2 different ways. I can use std get and then move the result of that function call to get an R-value reference to one of the items of the tuple, or I can move the whole tuple and then use std get on the R-value reference of the tuple generated by std move. Both of these techniques will move items out of a tuple. The first one allows you to decide which items you want to move, but you need to be careful in order to maintain the tuple in a valid state. The second one will instead cast the entire tuple to an R-value reference. std get has an overload for R-value reference to tuples that will move the item out of the tuple. Since C++ 14, as I previously mentioned, std get also supports retrieval by type if a tuple has no duplicate types. In this example function, I am again creating a tuple containing a foo, a bar, and an int. And then I'm using std get passing int as a template argument, and it will automatically find the position of that item inside the tuple and return an L-value reference to it. If the tuple had duplicate types, std get would cause a compiler error. Tuples can also be destructured by using the std_tie utility function. This is particularly useful when the function returns a tuple. In this particular example, the getT function returns a tuple containing a foo and a bar. Let's now assume that I already have an instance of foo and an instance of bar in my scope, and I want to assign both of them at the same time to the result value of getT. This can be easily done using std_tie. std_tie is a utility function that takes any amount of non-const L-value references. What it returns is simply a tuple of L-value references. std_tie is a utility that, given an arbitrary amount of non-const L-value references, will produce a tuple of L-value references from its arguments. In this case, calling std_tie with f and b will produce a tuple of foo_ref and bar_ref. getT
to the resultant tuple of references produced by stdtie will perform element-wise assignment from the foo and bar instances returned from getT to the ones pointed by the references in the stdtie tuple.
The returned tuple will then be assigned to the result of getT, so that every object pointed by the references will get its final result from the value returned by the function. Note that the objects will be moved out of the source tuple if it is an R value. Since C++17, we also have a new function called stdapply, which can be used to invoke a function with the elements of a tuple. And again, objects will be moved out of the tuple if appropriate. As an example, we have a very simple add function that takes two integers and returns their sum. Let's assume that we have a tuple containing two integers and we want to call add with the elements of that tuple. This is what stdapply exactly allows us to do. The first argument to stdapply is the function object that we want to invoke. The second argument is a tuple. What stdapply does is basically unpack the tuple for us and then perfectly forward the elements of the tuple to the function object we specified and call it for us. So in this case, if we have a tuple containing 1 and 2, and we call stdapply with add and that tuple, what we'll get back is 3, because add is being called with the elements of the tuple. Similarly, the standard library since C++17 provides another utility which is called makeFromTuple, which can be used to construct an object with the elements of a tuple. Let's assume we have a class called fooBar that can be constructed from a foo and a bar instance. And let's assume that we have a tuple that contains both a foo and a bar instance. If we want to build a foo bar instance out of the tuple, we can use std makeFromTuple, specifying the type of the desired object as a template argument, and then pass it our tuple. This again will basically unwrap the tuple for us inside a constructor called to fooBar, and then it will return a constructed instance of the class we desire. Tuples are very useful in generic programming or when writing glue code. They can also be used for quick prototyping or to avoid boilerplate when a simple wrapper is required. Additionally, they support lexicographical comparisons, which allow easy definition of by-member comparison operators. Let's assume you've created a struct or a class which contains multiple data members. What you could do is simply write out every comparison or equality inequality operator manually, but that causes a lot of boilerplate and repetitive code. Instead, you can use tuples to generate most of the code for you. In this simple struct called toInts, I have two int data members called a and b. And the way I'm defining the equality operator is by using stdtie. Since stdtie creates a tuple of L-value references, I have no extra cost here. The creation of the tuple will be very likely optimized away from the compiler. And I can tie both the elements of the current instance and both the elements of the right-hand side instance and simply use the equality operator on tuples to get the result I require. This can also be done with inequality and other kind of comparisons. Finally, let's take a look at move iterators. As you may know, the standard library provides a huge number of general-purpose algorithms in the algorithm header. These algorithms mostly operate on iterator pairs. Some new move-aware algorithms have been introduced in C++11. These are stdmove and stdmovebackward. Even though stdmove shares the name with the commonly used utility, it also has its own algorithm which works on iterator pairs. But most of the existing algorithms are unfortunately not move-aware. The solution to that is stdmoveiterator and stdmakeMoveiterator, which have been added to the iterator header. These functions allow us to adapt existing iterators so that they move upon the referencing. Let's see an example here. I defined a very simple predicate called has5chars, which takes a constant value reference to a string and returns true if the string has only 5 chars. In this function example copy, what will happen is that I will copy all the strings from the source vector to the destination vector by using the stdcopyIf algorithm. stdcopyIf takes an iterator range specifying the source and then an output iterator specifying the destination. In this case, the source is an iterator range of the source vector and the destination is a back inserter inside destination. It also takes a predicate and it will only copy the elements that match that predicate. In this case, my predicate is has5chars. Look at this example. What we're doing is basically consuming the items inside source to create a new vector called destination. Theoretically, we should be able to move from source to destination to avoid unnecessary copies. This is exactly what std makeMoveIterator allows us to do. By wrapping the source iterators with std makeMoveIterator, the objects that satisfy the has5chars predicate will be moved instead of copied. As you can see, the code is very similar, but instead of simply having begin and end of source, we will have them wrapped inside the makeMoveIterator function call. And this will guarantee that the items matching the has5chars predicate will be moved from source to destination. Let's now recap what we've seen in this video. Implementing move operations for your types allows your code to be faster, safer, and more expressive. The standard library provides a huge number of move-aware containers and utilities, which make use of move operation where possible, and some of them rely on move operations. Modern C++ libraries follow the steps of the standard library and will strive to provide move awareness. My advice is to always think about move semantics and move awareness when creating your own types. You will not only have performance and efficiency benefits in normal usage, but when using the standard library or third-party libraries, it is very likely that the move operation you defined will be internally used by those libraries as part of their implementation.